Welcome back to another video. Next, we discuss the rejection criteria in hypothesis testing, how we decide whether to reject the null hypothesis. In our example, the cutoff values 48.5 and 51.5 were chosen based on expert judgment rather than a formal statistical approach. However, this is not typical. Generally, there are two main methods for determining rejection. 1. Rejection region, which is a predefined region established based on a chosen significance level, alpha the same as type 1 error. If the test statistic falls within this region, we reject the null hypothesis. 2. P-value, which is the probability of obtaining the observed result, or more extreme cases, under the null hypothesis. If the p-value is less than alpha, we reject the null hypothesis. Both approaches rely on a predefined alpha, ensuring a controlled probability of type 1 error. In hypothesis testing, the rejection region is the range of values where we reject the null hypothesis in favor of the alternative hypothesis. The first step in defining the rejection region is setting the significance level, alpha, which represents the probability of making a type 1 error, rejecting a true null hypothesis. Common values for alpha are 0.05, 0.01, and 0.10. Next, we determine the test statistic, which is calculated from the sample data. We will be discussing the possible choices of sample statistics in following videos. Let's assume we will be using a standard normal, z, test statistic for now. The rejection region consists of test statistic values that are unlikely under the null hypothesis. For example, in a two-tailed z-test with alpha value of 0.05, the rejection region includes values beyond minus 1.96 and 1.96. If the computed test statistic is less than minus 1.96 or greater than 1.96, we reject the null hypothesis. Otherwise, we fail to reject it. As shown here, the rejection region changes based on the types of hypothesis test, or how we define the alternative test. For the same case of using a z-test, we can have a two-tailed test or two one-tailed tests. Depending on how the alternative hypothesis is defined, the rejection regions are different. For example, for a two-tailed test where the alternative hypothesis states mu is not equal to the mu0, we need to find the critical z-value of 1 minus half alpha, and the rejection region is anything less than negative z-value of 1 minus half alpha or greater than z-value of 1 minus half alpha. For a one-tailed test where the alternative hypothesis states mu is less than mu0, the critical z-value is z of alpha and the rejection region is any value less than z of alpha. Finally, for a one-tailed test where the alternative hypothesis states mu is greater than mu0, the critical z-value is z of 1 minus alpha and the rejection region is any value greater than z of 1 minus alpha. The p-value is the probability of obtaining a test statistic value as extreme as or more extreme than the observed value, assuming the null hypothesis is true. It quantifies the strength of evidence against the null hypothesis by measuring how likely the observed data would occur by random chance. A smaller p-value indicates stronger evidence against the null hypothesis. Given that p-value represent the probability of getting our data if the null hypothesis were true, and considering the fact that we always want to reject the null hypothesis in hypothesis testing, small p-values are what we want to see. If p-value is smaller than alpha, it means we have strong evidence against the null hypothesis, so we can reject it. But if p-value is larger than alpha, it means we have not enough evidence, and we fail to reject. Let's go over an example together. A company manufactures a type of battery, and historically, the average battery life is 40 hours. A new manufacturing process is implemented, and the company wants to test whether the mean battery life has increased. To test this, a random sample of 100 batteries is taken, and its mean is 42.2 hours. The standard deviation of battery life, sigma, is known to be 10 hours. We will conduct a hypothesis test at a 5% significance level. Please pause the video here and try to summarize the information provided here and write down the null and alternative hypothesis. Based on the question, We know that the average battery life is 40 hours, and the company wants to test whether the mean battery life has increased due to the new manufacturing process. So, the claim that the company is interested in testing is mu being greater than 40. We place this claim of interest in the alternative hypothesis, and as a result, our null hypothesis is mu is less than or equal to 40. We can realize this is a single sample z-test as we are hypothesizing on mu, the population variance is given, and we are working with a single sample. Plugging in values for mu0, sigma, sample mean, and sample size, our z-test statistic equals 2.2. But just having the z-test value is not enough. We should either use the rejection region or p-value approach to make a conclusion. We know our z-test statistic equals to 2.2. The rejection region for a one-tailed z-test, where the alternative is in form of mu greater than mu0, is from z-value of 1 minus alpha to infinity. In the rejection region approach, we compare the test statistic value to the rejection region. Alpha is 5%. The critical z-value is z of 0.95, which is 1.645, so the rejection region is anything greater than 1.645. Given that the test statistic falls within this region as 2.2 is greater than 1.645, we reject the null hypothesis. In the p-value approach, we compare the p-value to the significance level, alpha. To find the p-value for a one-sided z-test where the alternative is in form of mu greater than mu0, we need to find the probability of a random standard normal variable being greater than 2.2. That probability is shown in pink color. If the p-value is less than alpha, we reject the null hypothesis. Here, because our p-value, 0.0139, is less than 0.05, we reject the null hypothesis. You can see that why both approach provide similar conclusions. In the rejection region approach, we compare the z-test statistic value to the critical z-value of 1 minus alpha. We are comparing numerical values on the z-axis. In the p-value approach, we compare the probabilities, or areas under the normal curve. We compare the probability of observing something even more extreme than the current z-test value to alpha. In both approaches, the result would be the same because if the test statistic is in the rejection region, then the p-value would be less than alpha, and vice versa. The rejection region, also known as the critical value approach, and the p-value approach are two methods for making decisions in hypothesis testing. The rejection region, as the name suggests, compares the test statistic to a rejection region, determined from a statistical table. In this approach, we reject the null hypothesis if the test statistic falls in the rejection region. In contrast, the p-value approach calculates the probability of obtaining the observed test statistic under the null hypothesis and rejects the null hypothesis if this probability is less than the chosen significance level, alpha. While the rejection region provides a clear yes or no decision, the p-value approach offers more flexibility and a stronger measure of evidence against the null hypothesis, making it more common in modern statistical analysis. Despite their differences, both methods ultimately lead to the same conclusion. We will discuss these two approaches in more details. Thank you for watching this video.
See you in the next one.